I'd like to welcome my panelists up here onto the stage. Let me just introduce you one at a time. First on the dock is going to be Nirmal Villadaian. Yes? Close enough. Velayudhan. He's a senior director. Come on up, or Nirmal. And Arun and the rest of you, come on up and have a seat. Yeah, Joonyoung, come on up. And then I'll introduce you one at a time, and then we'll go over a few questions and then get right into the panel. Nirmal is a senior director for advanced projects at Viasat. Then we've got Joonyoung, who is a senior director at Samsung Research. We've got Arun Ghosh, a senior manager at Amazon 126, and also the comms systems lead at Project Kuiper for Amazon. And finally, Amitava Ghosh, who is the head of the radio interface group at Nokia Bell Labs. So I've called this panel session Extraterrestrial 6G. And that's because there's a working group inside the 3GPP that ended up referring to everything other than terrestrial networks as non-terrestrial networks. But we already had a perfectly good word for things that were non-terrestrial, which was extraterrestrial. Plus, next week, the House of Representatives is going to be holding hearings next Tuesday on unexplained aerial phenomena that have been stubbornly difficult to suppress or dismiss. So this is a time to think about extraterrestrial networks. Our focus today is going to be on networks that fly in the atmosphere or above the atmosphere. Anything not bolted to the ground is part of our focus today. And I have a few questions to start things off. I had thought of sprinkling these questions through the discussion, but Nirmal has sort of crafted his dialogue around these. And so I'll start off with the questions, and then Nirmal can go ahead and respond to them. First of all, the working group for non-terrestrial networks in the release 16 of 5G has put forward some recommendations for how to standardize these networks. But my question is, do these recommendations come too late? Are they, did the horse already leave the barn, in a sense, because we already have deployed satellite constellations, and the design of the waveforms for these constellations had to come years before the deployment. So what influence will these working group recommendations have on non-terrestrial networks, if any? And second, if this isn't the path towards standardization of these networks, then what is the path? There must be some path to standardization. Next, what is the asymptotic broadband downlink data rates we can expect? I recently read a paper that said it might be as bad or as low as just 2 megabits per second. And if that's the case, it will only be competitive way out in the hinterlands where nobody has even, say, DSL access. Or can we always compensate by launching more satellites, having more capacity on orbit, and get up to where we're 100 megabits per second or above and very competitive with terrestrial networks? Third question has to do with a company here in Texas called AST Space Mobile. They're not represented on the panel. I invited them to come, but they declined. They want to do something radical, namely to put up an extremely large spacecraft with something like 500 square meter phased arrays that can do direct communication with handsets. So whereas most low Earth orbiting constellations are talking to some fairly large antenna on the ground, and then you can perhaps pass data from there through a router to a handset, well, no, they want to go directly to handsets. And my question for our panelists, is that practical? And if not, is the problem a technical one or an economic problem? And next is a question about Google's Project Loon. The project went on for about 10 years with deep pockets funding it. This was an idea that Google had to send up high-flying balloons that would basically carry an LTE base station up at 100,000 feet, 60,000 feet, and then relay data down and offer direct connectivity to handsets. Loon was canceled, grounded in July or January of last year after a 10-year effort. Some of the most exquisite engineering. And the reasons why it was canceled are still in debate. But they put together a 400-page document of all the lessons learned from this effort. And I wanted to ask the panelists whether there were some nuggets of wisdom in that document. What lessons learned are more salient for NTN's extraterrestrial networks going forward? And finally, what is the future of space comms? Is it hybrid? Are we going to blend together geostationary satellite data, which is bulk and cheap, with LEO data, which is low latency but higher cost? Or is one of these two modes going to prevail over the other? Those are the questions to begin today. And Nirmal, you have the floor first, and then we'll go off to, I think it was Joonyoung next, then Arun, and finally Amitava. You'll have about 10 minutes to speak, and then we'll have a more free-form discussion with question and answer from the audience and between ourselves.
Thanks, Todd. Thanks, everyone, for having me over here. It's a pleasure to be here. So I've worked in the satellite industry for the past 22 years. Before that, I worked in the terrestrial industry for a little company. Qualcomm at the time was very small. And so I've had a sort of front row seat of what has gone on. And I thought I'd start with a little bit of history. So I don't know, I mean, imagine the majority of you guys in this room weren't around when the first cellular standard IS-3, or they call it now TIA 553, was actually started by Bell Labs in 1983. And then over the years, you went from analog FM modulation, you went to things like IS-54, IS-91, IS-95, which I had particular interest in. And you had the GSM, CDMA wars and all these things, and kind of settled down. But 3GPP wasn't really created till 1998. So it took about 15 years for everything to settle down. What you saw initially was the role of government and the auctioning of spectrum. First you had the A-band licenses and the B-band licenses. They weren't national, they were regional. You had the regional bells come in and try to aggregate things. And over a long period of time, this is how long we've been doing this, things have finally converged, right? Roaming is a real thing. You can actually take your phone, you go to Europe, and it'll work. You might pay a little more or a lot more, depending on your plan, but it actually does work. So the time scale for these things to happen is very long. So I think to address the issues that Todd is talking about, standardization, what is different in the satellite industry is that most of the big players are fully vertically integrated. They basically design their own networks. They design the payloads, design the satellites. Some of the panelists on here are very familiar with all those processes. And so you have these essentially closed systems. And it's tough to make predictions, as Yogi Berra said, especially about the future. So what is most likely, in my opinion, going to happen is that there will be consolidation, there will be standardization, but 1983 to today is a long way, right? So we have to get there. And we have to help create that ecosystem where things like this happen. So what I want to do is maybe talk about non-terrestrial networks and some of the lessons learned. I wish I could tell you that I'd read all 437 pages of the report, but I think I got up to about 100. And it was a fascinating report. I mean, they did a lot of soul searching. Why did these things fail, right? And they solved incredibly technically hard problems. The winds in the stratosphere follow a cyclic pattern going east-west and then switching directions every 2 years. So one of the problems you have to do in that case is that you have to have oversubscription, or you have to have many more balloons than you would actually need if the thing was actually stationary. And then, they had a problem with thermal radiation. So the equipment couldn't get too cold because it would be really cold in the stratosphere, so they had to solve those problems. And then you pay a weight and power penalty to get all these things to work. So they solved most of these problems. But what they found was that the capital needed to build these networks wasn't enough to generate enough revenue, enough free cash flow to actually maintain and operate these networks. So that's why after 10 years of trying, they gave up. So in the long run, as Kane said, we're all dead, but the economics of these systems matter. When, in the 90s, we were doing Globalstar. Globalstar was a low Earth orbit system, S-band, so at fairly low frequencies. What was amazing was that it took 4 or 5 years to build, but it fell apart in a year, right? And the reason was that there wasn't enough revenue from these systems to operate the networks. So that's the danger with all these things. I think one of the questions was, how do we see AST Mobile and players like that come in? One of the fundamental questions raised in one of the papers you sent was, what is the capacity density? Like, how many users can you support per square kilometer? And it turns out that if you actually don't have the ability to focus your capacity on where the demand is, then the business models break down. Let me give you an example of what that means. If you look at the average revenue per user in a terrestrial network in the US, you go to T-Mobile, their premium plan is about $140, I believe. And you're paying, on average, about $1.50 per gigabyte. Now, if I go to India, I'm originally from India, I visit there every year, I can get a gigabyte of data for about a quarter, right? So there is almost an order of magnitude difference in the willingness to pay for the data. So now you go and look at these business models of all the companies, they have to invest in things like base stations, infrastructure, and you go and you look at the free cash flow models of these companies. Take a company like Verizon, where does it all end? Verizon has got revenues of north of $100 billion a year. Their margins are about 15%. It's a healthy business. It's got a good yield, right? That is sort of the end state of some of these businesses using conventional business models. So you're basically selling bits. If you really want to monetize these networks, you need to be able to find applications that some of you have addressed in today's talk that can actually do those kind of things. The other thing to remember about LEO networks is that space is really a finite resource. So there is only a certain number of orbits that will actually be viable, and a handful of players are going to have to basically shake out of what's going on. We're not saying that, LEOs or GEOs, that's not a debate that I want to wade into, but there is room for these networks as long as the unit economics work. But if you think that we have room for like 5 or 10 players, probably not, right? So then the last question, I hope I'm doing okay on time, is what about hybrid LEO and GEO networks? Let's talk about the physics of the problem. It's a little different. Say geostationary satellite is about 26,000 miles up in space, and LEOs are somewhere in the, couple hundred kilometers to 1,000 kilometers in space. So the translation of that problem is, if I want to get the equivalent performance given my payload and power budget, my antenna needs to be about 6 or 7 dB per Kelvin better for a GEO than a LEO, okay? So I'll leave you with that, but if you think about that, then the question of, cheaper GEO bits versus lower latency premium LEO bits is really one of what are the use cases that would actually call for those kind of unit economics. And so I just want to end with that. So.
Thank you, Nirmal. Provocative. We'll unpack some of that during the discussion. Joonyoung, would you like to take the floor?
So here's the timeline of ITU IMT for 2030 and beyond, which is actually a kind of official name of 6G used in ITU, and also 3GPP standardization timeline. So 3GPP first developed NTN standards during release 17 timeframe. The release 17 3GPP NTN, okay, thank you. Standards mainly focused on specifying features to enable 5G NR in non-terrestrial network with addressing key satellite issues such as long propagation delay and high Doppler, and also moving cells due to the movement of satellites around the Earth. And release 18 NTN, which is just starting, will work on performance enhancements, especially for handheld terminals, and also UE's mobility between terrestrial and non-terrestrial network. And also 3GPP will try to extend and enhance some current NTN features. Then why did 3GPP develop the NTN standards on top of the one for terrestrial network? So NTN is indeed a key enabler to make 5G and 6G service available anywhere and anytime. Here we have panels from Amazon and also Viasat. So big satellite players plan to launch satellites and provide broadband connectivity to underserved or unserved community in the world. And also NTN will provide connectivity to any platforms, whether it is located on the ground or on the sea or in the sky. And also NTN can work as reliable backup network, especially in the disaster situations where terrestrial network can break it down. Then as for applications of NTN, so IoT connectivity and also uploading to NTN from TN, and also broadcast service, and also cellular connectivity in the platforms located on the in the airborne or the maritime situations. Then on this slide, the next slide, so I tried to cover what tools have been implemented in the 3GPP standards. So target scenario of release 17 NTN is transparent payload, which is also called as bent pipe architecture. As we see in the figure, actually base station is located on the ground. Then satellite will mainly work as a RF repeater without so L1, L2, L3 protocol capability. So those things, those protocol capability will be handled by base station on the ground. Then satellite will provide hugely extended coverage. In some configurations, actually, one LEO satellite can cover entire Austin area. Or in some other extreme scenarios, one satellite may cover entire Texas, although I'm not sure whether it will happen or not. Then another important assumptions are in order to deal with long propagation delay and large Doppler, so UE is assumed to have GNSS capability, and also satellite ephemeral information such as satellite trajectory and speed will be provided to the UE. Then that UE can calculate the propagation delay and the Doppler. By the way, how much time do I have? Just 1 minute. Okay, I'm so sorry. Then in order to deal with propagation delay incurs multiple problems during the UE procedure for initial access, and also the hybrid reality operations for data channel transmissions. So in order to deal with the issue, the random access response time will increase for NTN situations, and also the base station configured to HARC enabling or disabling. And for network size, I will just spend 2 minutes. So on the network size, two issues are illustrated there. One issue is because NTN is located in the satellite is located in the very high altitude, then the propagation loss experienced by near UE and the far UE will not be that different. So instead of just relying on signal strength-based measurement and mobility, so UE distance from serving cell will be additionally utilized to determine whether they perform handover or not. And another issue is the satellite cell is moving with due to the movement of a satellite. So in order to handle that, kind of a quasi-Earth fixed cell notion is introduced in 3GPP. Then UE will perform measurement operations for a given time window. I think that's pretty much it. Thank you.
Thanks, Joonyoung. We'll have now Arun.
All right, I realized, Todd, that the way I had put my slides together, I do answer a few of your questions. So I'm going to go a little bit off script here and maybe stick to just the first couple of slides and try to have a dialogue around that. Okay, if you can go to the first slide, please. Oh, I've got the control here. There you go. I always like to ask this question. Hasn't LEOs been tried before? And as you know, Global Star, one example, Iridium, Teledesic, we have all tried. The amount of success has been not worth mentioning. So what is different now? Why there's a lot of interest, and companies are interested in launching mega constellation. Many of them are already up there. There's a lot of interest in 3GPP to have non-terrestrial or extraterrestrial networks as a part of that. But why do we think this is the right time? Besides ET being able to call home or phone home, what is it now? And maybe I'll ask you, Todd, what's your view? And there's no wrong answer. I'm just curious to hear, what people think is the reason for us to think that we will succeed this time.
So you're saying we're living in a graveyard of Iridium, Global Star, even Loon is now rest in peace, right?
Yes.
And what's different now, especially given that Loon was only mothballed, a year ago. My quick answer, Arun, is that previous projects were only half crazy, and they need to be full crazy. So
I like that.
it's built into the name Iridium.
Yeah.
Iridium was built with 77 satellites. It later went to 66, but nobody calls it dysprosium. And at the time, that was crazy. That was absolutely outrageous to think that we could field that many satellites. But now what we've got is full crazy. We've got thousands coming and thousands already up there. I think it boils down to reliable and cheap launch capability.
Bingo. If you can go to the, actually, why am I saying this? I should be self-sufficient. That's right. That is precise. And we often forget that, and that is not a trivial part. So you're right. Before we had problem with, tens of, satellites. Now we're talking thousands, maybe even tens of thousands. So what makes us think, that we can actually put up that network? And this comes back to the same question, is it financial business reasons that held us back, or is it technical reasons? And my premise is that the two are not independent. Two are actually highly dependent, because it is technology that actually makes business often possible that is not possible before. So one of the fundamental things that I believe that's a strong driver as to all of this is the cost of launching a satellite. Something that used to be hundreds of millions of dollars of launching a satellite is now in the range of 1 to 2. So now, and that actually has a profound impact, not on just the scalability of the network. And as I will walk through some of these other points, I'll try to make it further, clear as to why that launch capability is an important, besides being able to launch a large number of satellites. And it's a fascinating, technology, how these reusable rockets, that can vertically land, and it looks great, but it's not an easy technology to actually build. And when I see that, one of the things that comes to mind, I saw this a long time back. In fact, one of the demos from one of our AT&T Labs colleague is the concept of inverted pendulum. And they were actually using AI-driven engines to actually solve the problem. They actually had a demo of a two-dimensional a pendulum with 2 degrees of freedom, and they could balance it inverted. It's kind of the same thing that you have to do with the rockets, right? So it's technology. It is a lot of the capability of self-monitoring and self-AI, that allows you to build that technology. And that reduces the cost of launching a satellite. And obviously, the other thing that happens is that because of development in power systems, in battery technology, as well as silicon technology, you can now put in a lot of bandwidth in a relatively small amount of satellite. So think of a satellite that is about the size of a fridge, and that too not a very large one, just a regular household fridge that has capability of serving 50, maybe 100 gigabits per second of traffic on the ground. That's a lot. And because these satellites are relatively closer to the Earth, that means the amount of footprint that they serve is not very large. So now you're talking about 100 gigabits per second of capability on a single satellite that can be focused on a relatively small area on the Earth. So this actually ties into the next question, is that, okay, you have so much capability on the satellite, can you deliver that to the ground? I heard something like a couple of megabits per second, but I don't think a couple of megabits per second would interest anybody. Even if you don't have the bandwidth anymore, the expectation of things like that you do on the network, like Netflix servers, if you watch Amazon, Prime, they don't care whether you have 1 megabits per second. I mean, everything on the internet has proceeded to develop to assume a much higher bandwidth. So a megabit per second will not entice anybody. But there's one thing that, having worked in the satellite business, I have realized is that in a terrestrial network, you can boost up your power, and you get a stronger signal, and you improve your SINR, and you get higher throughput. It doesn't quite work that way in the satellite, and the reason is regulations, is because these spectrums are inherently shared. So what that means that there is a maximum power flux density that you can actually put on the ground, and you cannot cross that, and you have to stay within that. So spatial reuse becomes extremely important. And that's why I think phased array technology has been a huge enabler of all of this. And what that means is that before, if you had to shine a beam, it would be very wide. But with phased array and larger apertures, what that means is that you have the ability to reuse your entire spectrum multiple times. So even if you are limited by the power flux density that you need to meet on the ground, you are able to reuse your entire resources many times over. You can reuse it 16 times, 24 times, 32 times. It's a large number of beams. These phased arrays, that these satellites use are a completely, I would say, in a completely different scale than what 5G base stations use as phased arrays. They have an incredible capacity of reusing the entire spectrum much more densely. So that allows you to actually take that 50 or 100 gigabits per second of capacity and actually, put it on the ground and still meet the demand. And there's one thing I did promise, and I'm going to tie back, this cheap satellite, lower cost satellite, low Earth to the whole standardization process. Standardization is definitely helpful. It has its own pain. Those of us who have been in 3GPP can certainly attest to that. But it is worthwhile. And there's a reason we actually try to do that is because of the economy of scale that you can achieve with that and the interoperability. It's eventually good for the customer, right? At the end of the day, you can get a phone and you can have complete freedom of choosing what phone you take and what network you get on. And that's what we want to do too. The satellite business needs to go in that direction if you really want to take advantage of economy of scale. So standardization is a good thing, but if you want to keep up with 3GPP, you have to realize that you have to be able to recycle your hardware at a certain scale, at a certain period of time. So 3GPP comes up with a new generation of technology every 10 years. But even within that new generation, what I have seen in my past life is that base station hardware would get recycled every 4 to 5 years. And that's how you keep up with technology. That's how you keep up with the new things, the new features that are developed to be actually implemented. You need that capability, which is very different from what the traditional geo-based satellite world operated. These satellites were hundreds of millions of dollars in cost, and they were put out there and they stayed for a very long time. We kind of reversed that whole premise with LEO systems and the way this is going. The satellites are becoming cheaper, they're becoming much larger in number, and they don't have a lifespan which is more than 5 to 7 years. That means it gives you an ability to recycle your hardware and keep up with these new features and keep producing more and more enhanced features, whether that's lower latency, better throughput, better reliability, higher speed, higher mobility. So I think my honest belief is that a lot of the pieces of the puzzle are in the right place. We have technology both on the software side as well as on the hardware side to really scale this thing and make it evolve at the same pace, at the same rate as the terrestrial system. Then you have to sort of do that. My view is that these two systems really have their own strength, and one can complement each other. But you still need that seamless experience from a usability and use case point of view. So I think in many ways time is right. I think this is a very exciting time. I always like to draw analogy, and my analogy is that when it came to IoT was an add-on onto LTE. When LTE was designed in the beginning, we never thought of IoT, but we added IoT as through NB-IoT, EMTC. But when we came to 5G, we actually baked that concept and things like device-to-device right into the technology right from the beginning. NTN is kind of doing the same thing, although a generation later. NTN got added to 5G as an add-on, and I think there are plenty of things that are wrong with the current NTN design, but it has gone that way for a certain reason because it was added on. My hope is that with 6G, we take NTN as a part of the design right from the beginning and address all the problems that are there. So I know I didn't address all the questions, but maybe touch on a few of them, and we can get to more of the discussion during the interactive session. That's all from my side. Thank you.
Arun. Next we have Amitava Ghosh, and he may or may not have slides available. We'll see. Looks like, yes, good. Thank you.
Okay, so the slides are available. So one thing, Todd, you missed is a question. What is the probability of having 2 Ghoshes in a panel? Yes, it's very rare. Okay, so I think all the previous speakers have answered most of the questions. So you see, NTN is not only about LEOs, it consists of GEO, MEO, LEOs, HAPS, and LAPS, you see. So my interest is in the HAPS and the LEOs currently. So all these LEOs are being standardized with HAPS, you see. It is able to operate with the current NR or LT specifications. So, and you have various use cases, disasters. So Joonyoung already mentioned that. I will not go through it. Various use cases, very promising. The main use case is to bridge the digital divide, you see. So that's one of the critical use cases I have, and in addition to public safety and disaster scenarios. So what are the main things? So how do you develop the ecosystem? So you see, LEO HAPS to commercial 5G handsets. That's the key use case. That's the key, and you see it is very difficult to satisfy that use case. We have LEO HAPS to premise broadband services for fixed services. That is a possibility. Starlink is providing that. And GEO LEO for high speed. So my main interest will be LEO HAPS to commercial handsets and LEO HAPS to premise broadband services. The extraterrestrial networks you are talking about, it is servicing the moon. Nokia was able to deploy, or they plan to deploy this LTE network in moon. And now I read in Spectrum also, they are deploying satellites in moon to cover the moon and Mars. You can do that. Okay, so that is extraterrestrial networks. So, so this is the technology. So we have the service link, you have the feeder link, and you have the satellite to satellite or HAPS to HAPS link. So these are the various links you have. So the key is to find the right combination of aerial platform service and feeder link technology and mass market for viable business case. So basically the Loon was right. The key impediment to deploying all this NTN is the business case. We have studied it in Nokia, and we are continuously evaluating the business case. It is difficult to bring the cost per gigabyte down. So I'll say that is the main. Technology can be solved, you'll see. It's not a big deal. The business case is the main thing. So you can have sub-6 gigahertz, mainly for the access link. For the feeder link, I think millimeter wave spectrum is very promising. And for the inter-satellite links, it can be optical links or millimeter wave links. So that is the upshot of this slide. And I like to, I don't know whether it is not coming out right, but this is a link budget. And this is the issue we have. So the top one is LEO HAPS for fixed service. You can get hundreds of megabits of service with the link budget because you have 43 dBi of antenna gain, no problem. The issue is with the LEO mobile data uplink and downlink. You see, mainly for the uplink, the data rates are lower, you see. And that is, the physics has not changed, right? So you still have the long distances, you have the, and this is all to commercial handsets, you see. If you have large handsets, that may change, but so I think the most promising case for LEO will be global IoT service. That's where the IoT services are low data rate. And I think it makes sense for global IoT and voice services. But EMBB is challenging. EMBB is challenging. But HAPS for both uplink and downlink is a little bit better because the HAPS flies at an altitude of 20 kilometers. So you get a better data rate with HAPS. So, and then Joonyoung talked about transparent and bent pipe architecture. I will not go through it. Loon was a regenerative architecture. The current standardized in 3GPP is bent pipe or transparent architecture where the base station is in the ground. But regenerative architecture has some advantages, which will be probably in standardization, it will be in release 18, release 19 kind of time frame. And this is the kind of comparison between bent pipe and regenerative architecture. Like in regenerative, you need the space hardening of the base station, right? Because it has all this ultraviolet radiation and also This shows the advantage and disadvantages. The next is, so this is for the HAPS. The main issue is both for the HAPS and the satellites, how to design your antenna, and Arun touched it. And we designed this 7-cell system for HAPS. And you see, this is the kind of, for a 20 megahertz, 2.1 gigahertz, 7-cell with 100-kilometer radius. This is the kind of spectral efficiency we are getting. Not bad, but but the issue is with the spectrum availability for these bands. And so with 20 megahertz spectrum, you can get 26 megabits on the downlink. Uplink is 14 megabits. Edge users is pretty low. So 3GPP status, I will not touch it. What I will say, there are companies like AST providing proprietary solutions. So 5G deployment using satellites require proprietary hardware solution or release 17 or release 18 NTN support. So HAPS can work with legacy LTE and NR specifications, which I already pointed out. So HAPS is a better option. Launch cost is, there's no launch cost. Basically, I have seen HAPS and plane being launched by hand. You see, you can do that. So that's one thing so there is no launch cost here, basically. But there are various kind of platform for HAPS. You have this hydrogen power plane, solar power plane, but the one I saw by Zephyr, it can be launched by hand. So last slide, global coverage is one of the advantages of NTN, but you have to look at cost, power, and energy efficiency, and how to improve the coverage on uplink and downlink. The main issue is how to improve the antenna design, number of cells, etc. We have to work on the ground station feeder link and inter-satellite links or inter-HAPS links, which are essential components of the end-to-end network. UECP requirements. I think to take advantage of the ecosystem, you have to use commercial UEs, but you can do very little with commercial UEs for EMBB, global, and for IoT devices, it is a non-brainer. Spectrum, access and feeder link, inter-satellite, inter-HAPS link, we have to think about the spectrum too. So I'll say, and the interaction between terrestrial and non-terrestrial networks. So you're moving from a terrestrial network coverage to a rural area. So that continuity of coverage, you have to work on that. And so I think NTN will always be a complementary solution to terrestrial network, and it has to have the right business case. Maybe I think in the 6G timeframe, the cost of the equipments and the platforms will come down, and it will happen. But it is a challenging proposal to make NTN effective by 2025, 2026 timeframe. Maybe by 2030, it is viable. So that's all I have.
Thanks, Amitava. So these are some excellent provocative introductions. We've got about, Jeff, can we take 10 minutes at least? No, we've got to 20, right? All right, so good. We're gonna have a 20-minute discussion here. I'll kick it off, and then I'd like you in the audience to be thinking about questions you might ask our panelists, and we're happy to entertain your Q&A too. I'll kick it off with a question to Arun. You mentioned that maybe we can bake in the NTN protocols into 6G. Where is the toehold? Where's the first start? Is it that we try to look for standards for direct to handset links for these, for IoT, which I think Amitava persuasively argued that it's mostly going to be text messaging and maybe a little bit of voice, but not the standard downloading of video. Is that going to be the toehold? Because really, there isn't much to say about a network that goes directly to a larger piece of user equipment and then broadcasts out via Wi-Fi through a router. I mean, those can exist orthogonally, just as Starlink is doing today. It doesn't require any attention from 3GPP.
Right.
Right?
Yeah, you're right. It's it's not a big enough business case, or it's not enough use case to justify something to exist on its own. My guess is that at some point NTN does need to address connectivity to handheld kind of devices. I think it does need to address that question. To handheld devices like a phone or something that's reasonable, that's portable and mobile, and maybe a phone or a tablet or a laptop, something like that. And the reason is, and you can see that the approach taken by a company like AST in science has been to generate a very large phased array in space. But very large phased arrays have issues, and I was talking to Charlie about this one a little while ago. You get into engineering issues. How do you calibrate such a large phased array? How do you do timing synchronization? Because timing synchronization errors start to become more and more important as you start to put in more and more elements. And don't forget that thermals is a problem in space. So these things, you want to make them lightweight, so you make them very thin. But when they get heated up, they actually end up twisting like a potato chip. So how do you make a phased array out of that? I think a better concept, and this may be the same lesson that Charlie was referring to in his talk, is to, instead of having a single large aperture on a single satellite, you try to actually synthesize a larger aperture, taking advantage of multiple satellites. It's been done for decades in radio astronomy, and so
on the ground it's been done.
On
yes.
the ground it's been done.
Bolted to the ground.
Yes, but the problem there was astronomically much harder, no pun intended, than what we are trying to do here.
In that they're working with extremely weak signals.
Yes, absolutely. And so I think it is definitely possible. It is, in my view, it is one of the subjects that we have to address. How do we actually synthesize a larger aperture to allow for something on the ground that's a bit more concrete? And I think, as you know, the hard part is really the uplink. The uplink is always been the harder one to close down. But the downlink can also be challenging because of these PFD limitations in some of these bands. But those may be regulatory limitations. They may change over time. But you still have to, in my view, we still have to address that use case. Otherwise, the business is probably not going to stand. Or there's, and not just that, I don't think there's going to be enough interest even in 3GPP. So if you saw how 3GPP NTN, I mean, it's a great piece of standardization, but it used to be a very small group, when it got started. And, we used to even, joke about it, saying that, sometimes they may not even have a room to actually make their discussions. And now I feel bad because I might be in the receiving end of that one. But yes, so to get to more and more people interested, you have to get the bigger part of the ecosystem involved in that. So my answer is yes, it needs to address that, and we have to figure out how we can do that.
Joonyoung, do you agree that this is a good starting point for standardization, say in 6G, that we would focus on the link directly to the handset, even if it's a low bandwidth link?
Yes, I think so. When people say about 6G, we say, even I said that connected anywhere, anytime, when I'm taking a flight or on a ship on the sea, or I'm traveling around with my family in a certain quite deserted area. Actually, I enjoy visiting a national park in the US. Then, without satellite support, I cannot have a cellular connectivity to the network. Then, actually, satellite can provide that.
Sure, sure. And you don't want to be having to carry around an antenna that you pull off of your belt and unfold
Yes,
and point toward the satellites and make sure that, yeah. Okay, I'm happy to take questions now from our studio audience here. It looks like Sanjay has one.
So this is a question about how sustainable this is in the following sense. If you have a 50,000 satellite cluster up there, and you're assuming a failure rate of about 2%, which is what you see in data centers, then we are talking about 1,000 satellites replacement per year. This is okay if you're going to manage a 50,000 cluster, but these are random. These are not scheduled. So you need to basically replace 3 satellites every day at random locations. How do you manage this kind of, does it make it cost ineffective then?
Good question.
I can take it. Yes, you're right. There's a certain amount of failure you have to account for, and the failures is not just always zeros and one. You can have partial failures, right? Thing can be operating at 1/4 the capacity. I don't think you try to move a satellite to even out the constellation. I think it's a little bit of a misnomer that constellation is very uniform. It actually is not. And even if you are, so depending on where you're on the ground, if you look at what the constellation looks above you, it can often be very non-uniform. So I don't think uniformity or replacing of the satellite is actually necessary. From what I have seen, most of the time we design constellations in such a way that you can tolerate about 5 to 10% random failure and still maintain coverage. You will have to take a hit on capacity, but you want to keep the coverage alive. And these could be all random events. So you need to factor that into the design itself, and you need to have enough smartness on the network to adapt to it when it does happen.
Yeah, good question.
One of the opposing view I have, why not HAPS, you see? The Germany can be covered with 6 HAPS, Japan, whole of Japan by 10 HAPS. And you can launch the HAPS anytime. You can bring it down after 6 months, change the equipment. It is much easier. The whole of US, and HAPS can cover 100 to 200 kilometer radius, right? So why not do that? And it has a better, it can cover, you can use commercial handsets. It has a better link budget than satellites. And you can do without changing the spec at this point of time.
So when you talk about HAPS, I'm assuming you're talking about high-flying drones instead of balloons, because balloons have been tried, and the business case was not there, right? I don't think anybody would doubt that Loon put in a valiant effort. What's different about high-flying drones that makes this more economical?
So the HAPS can be, the platform can be balloons, where it is very difficult to control the trajectory of the balloons. Or it can be solar-powered planes, or say hydrogen-powered planes, you see. So these are the, which can fly in stratosphere, right? 20 kilometers above Earth, you see. But I think the cost of the platform has to come down. Then it becomes economically feasible. So unless the cost of, we go after 5, 6, 10 years, the cost will come down like any other thing, right?
Do any of our other panelists have opinions on HAPS, on their long-term prospects? This is high-flying drones mostly.
Yeah, I don't have an opinion. I have never worked with them, so I would be wrong to actually express an opinion. But one thing that does come into mind is that unlike satellites, yes, there is a launch cost to it, which has dramatically come down. But once you leave them there, they pretty much stay there. You don't have to spend anything. The amount of rocket fuel that you have to use, or fuel that you have to use to do station-keeping maneuvers and keep yourself within the station-keeping box is really minimal. But that's not true with HAPS, right? You have weather patterns, you have to, so I don't know. I have no idea how the business case works, so it'll be wrong of me to express an opinion, but I know it has been tried and it's been less successful than LEOs so far. Yeah.
Yes, but LEOs were less successful than they were expected to be for 20 years, right? So
true.
We can cut them some slack.
Yes. Yeah.
Joonyoung, did you have?
Right. So from
Speak into your microphone.
Yes. From a technical perspective, some benefits of HAPS is it will be much easier to support mobility. In case of LEO satellites, it moves with a speed of 6.7 kilometers per second.
Yeah, about 7 kilometers a second.
Yeah, so actually handover is required every 6 or 7 seconds.
Yes.
And therefore, in our scenario, there will be so many UEs. All those UEs need to perform handover.
Yeah.
There will be a lot of signaling overhead for that.
Handover with LEO is more like on the order of 1 minute or 2 minutes.
Yeah. But those are all group-based handovers. So you don't unicast those information because all the UEs, they all go together. So yeah, you need to design handovers that are a bit more group-based, because instead of doing unicast.
Well, at least if we in case of HAPS, that overhead will be smaller.
So you have to do both delay compensation and Doppler compensation, right? So for HAPS, you don't need those. HAPS flies at 120 kilometers an hour. So, and there is no delay, it is 20 kilometers.
Yeah,
So-
there's no question there's some real benefits. I'm wondering about mass production. It's much easier to build a satellite the size of a refrigerator in mass quantities than an aircraft the size of larger than this room in large quantities. They have to have an incredibly long wingspan and be very light to sail aloft with solar power only. Other questions from our audience? They're in the back, yes.
Thank you. Yeah, and we have a panel of all the experts here who has been designing a cellular system for many, many years. So when we design cellular system, we know that we mostly care about three things: coverage, capacity, latency. So can you make a comparison between the extraterrestrial system with terrestrial system in terms of coverage? So what technique are you going to introduce in 6G to significantly change the coverage gap, right? So we talk about large array size. What else? Or distributed array. And the second is capacity. What's the cost per bit gap? How many order magnitude are we off right now? When you compare state-of-art extraterrestrial system with our cellular system, are we off by 3 order magnitude, 4, 5, in terms of dollar per bit, right? And the third one is latency, of course. I think with LEO, we know how much latency there are. Is there any way you can improve latency? And of course, all of these are for both for feeder link and the service link, right? So essentially there are 6 questions for you guys. Is the launching of huge number of satellite, is capacity increased linearly with the size of constellation, or it's super linear? You're also gaining something else. So that these
Nirmal,
are.
do you want to take
Yeah,
a
sure.
crack
This
at
is a great question. Great 6 questions. So I'll try and answer some of them to the extent that I'm allowed to. So let's talk about the sort of capacity. What Viasat is in the process of doing is launching 3 geostationary satellites that will cover the entire globe. So that's the coverage part of it. The capacity of each satellite is greater than a terabit per second, significantly greater. I can't tell you how much. And what was some of the other questions? Latency. Latency to a geo is somewhere in the order of 600 milliseconds round trip. That's just not the round trip delay. There's other stuff that goes in because of the IP protocol. So the response to, okay, what do you do with such a huge latency when compared to LEO, is the majority of traffic on the internet today is fairly latency insensitive. We're talking about traffic such as video, for example, that is latency insensitive. So we believe that the bulk of the traffic can be, bulk of the applications, very high percentage, can be addressed by geostationary satellites. Looking at the financial side of things, to launch a single geostationary satellite, thanks to the valiant efforts of some of the people here, their launch costs have come down. We've been able to leverage that. The cost of the satellite is, each satellite is going to be somewhere between, I can't give you exact numbers, but $500 million to $1 billion. So for, significantly less than $3 billion, you can cover the entire globe with more than 3 terabits per second of capacity. So that's my story.
Okay, it is true that the bulk of traffic is latency insensitive, but if I look at a particular user during his or her day, there will be moments where latency becomes important. A video conference call,
sure,
or some remote teleoperation will be puncturing the day with these with these lower latency intervals.
You're absolutely right, and I think that's the great opportunity for us to work with LEO systems or other NGSO systems, non-geostationary systems.
But the beauty would be if there was a kind of unified framework so that the same terminal
Absolutely.
worked for both.
Absolutely.
And I assume that's in the Viasat roadmap.
Well, what I can say is that we have been vertically integrated for all of our life, and so are all the other players of note in this space. And I don't see that changing. Yeah, I talked about timescales when I was, so eventually it would make sense because of economies of scale. Right now, we don't really see any benefit to standardization, and something needs to change. There has to be, so the way we like to think about this
Are
is,
you posing this as a problem, as in we don't see a benefit to standardization, this is a problem we've got to overcome, or you're just stating a fact?
it's a fact, it's also a problem, but what I would say is that the way to solve that is really to learn from the lessons of the cellular industry, which is you needed to roam, right? You wanted to have your phone work in New York as well as you wanted to work in California, right? And you show up and there's a GSM network and there's nothing over there. So you had to create that interoperability. And we're going to need to do that, but at this point, there is no incentive to do that. And I sincerely hope that it changes. So.
Yeah.
So I can add to that. You see, for geos, you don't have the Doppler problem, right? So you have the latency problem, but you can work with, and I saw a very good report, with NR or LT. By changing the timer setting, you can compensate for the latency. So the geo can work with traditional IoT, LT IoT, narrowband IoT, or LTEM easily. But again, the problem is very high data rate. EMBB can't be supported with the legacy terminals. Yeah.
Well, one of the things I want to impress, and we'll have to stop here, but I want to impress on your minds, especially students, is the radical requests that are being made up here. I mean, you heard Arun talk about synthetic apertures with multiple satellites in low Earth orbit to overcome the path losses to a handset. That is an enormous engineering challenge that will require the best minds of aerospace and electrical engineering. You heard Nirmal talk about ways of fusing GEO and LEO in the same in the same vertical. That again is going to be a challenge. This is going to require the best of us going forward, and yet there's no other way to get global coverage than probably something that has to do with extraterrestrial networks. I thank all our panelists, and I hope that you'll look for conversations with them maybe at lunchtime and later in the day. Thank you.
Thank you.